Meet Ernest Rutherford, the pioneering Kiwi who transformed our understanding of the universe. Born the son of a New Zealand farmer, Rutherford rose to become the undisputed pioneer of the nuclear age. Through groundbreaking experimentation, he famously discovered the atomic nucleus and became the first to split the atom, shattering long-held scientific beliefs. His revolutionary work did not just reshape physics. It fundamentally ushered in the era of big science, paving the way for large-scale, collaborative research that defines modern technological advancement. This is the extraordinary story of how a boy from a rural farm fundamentally changed the world forever. Welcome to the three great acts of Ernest Rutherford's legendary career, charting his rise as the greatest experimentalist since Michael Faraday. In Act 1, the McGill era, Rutherford proved that radioactive elements spontaneously decay and transmute into entirely new substances. Moving to Act 2, the Manchester era, he shattered accepted models of matter, revealing the dense atomic nucleus and successfully creating the proton, illustrating how scientific breakthroughs build on each other across eras. Finally, Act 3, the Cavendish era, saw him transmute science itself. He elevated physics from modest tabletop experiments to the collaborative, heavily funded era of big science, inspiring future large-scale scientific projects like particle accelerators and nuclear research facilities. Trace the remarkable journey of Ernest Rutherford from the rural landscapes of Brightwater, New Zealand, to his role as a pioneering scientist, inspiring curiosity about his roots and achievements. His origins lie in Brightwater, New Zealand, where a childhood of rural farm resourcefulness prepared him to earn 3 degrees. In 1895, the prestigious 1851 Exhibition Science Scholarship became his breakthrough ticket, allowing him to leave New Zealand for Europe. This punched his ticket to an apprenticeship at Cambridge's Cavendish Laboratory, where, in 1911, he proposed the nuclear model of the atom, making him the first non-Cambridge graduate accepted to conduct research under J.J. Thomson. Rutherford never forgot his roots. When later elevated to the peerage, he proudly incorporated a Kiwi and a Maori warrior into his official coat of arms, inspiring pride in his heritage and achievements. Before decoding the atom, Rutherford conquered the airwaves and mapped the anatomy of radiation. Using his innovative magnetic detector, Rutherford demonstrated remarkable skill in electromagnetic wave detection, setting a world record for distance of half a mile, highlighting his pioneering contributions before Guglielmo Marconi outpaced him. Shifting his focus to radiation, Rutherford dissected its core components, revealing how alpha and beta rays contributed to the understanding of atomic structure, laying the foundation for modern nuclear physics and medical applications. By visualizing how these distinct rays deflected in magnetic or electric fields, Rutherford laid the critical groundwork for modern nuclear physics, demonstrating his profound influence and inspiring confidence in the importance of scientific discovery. Step into the McGill University lab, where modern alchemy was born. Working alongside Frederick Soddy, Rutherford triggered a monumental paradigm shift by proving radioactivity is a subatomic process. They revealed that atoms spontaneously break apart, eject mass, and transform into entirely new elements, such as uranium decaying into thorium. During these experiments, Rutherford's discovery of radon reveals how solid thorium emits a highly radioactive, short-lived gas, an exciting breakthrough that underscores the surprises hidden within atomic science. To quantify this, he introduced the concept of the half-life, a remarkable idea that provides physicists with a reliable cosmic clock, helping us understand Earth's age and the universe's history. Behold the accidental chemist. In 1908, Ernest Rutherford was awarded the Nobel Prize in Chemistry for his groundbreaking investigations into the disintegration of elements. At the Nobel banquet, Rutherford humorously remarked, "I have dealt with many different transformations over various periods, but the fastest was my own shift from physicist to chemist in a single moment." The irony was in the committee's politics. Rutherford received 12 nominations for physics, and only 4 for chemistry, yet the physics committee rejected him, claiming radium was chemistry. Despite 11 additional physics nominations, he never won a second Nobel Prize, highlighting the complex nature of award politics. In 1909, physicists experimented with firing artillery shells into tissue paper. Based on existing models, they expected that 100% of the alpha particle bullets emitted from a lead box source would pass effortlessly straight through an ultra-thin gold foil, just 0.6 micrometers thick. However, the actual results were surprising and challenged that assumption. While observing the results through a microscope, researchers noted scintillation flashes occurring at sharp, unexpected angles. Most astonishingly, some particles bounced back toward the source. This significant discrepancy between expectation and reality revealed that an atom's mass is not spread out but concentrated in a dense, positively charged nucleus, fundamentally altering our understanding of the microscopic universe. This visual illustrates a significant paradigm shift in physics, the overthrow of the plum pudding model. On the left, J.J. Thomson's initial hypothesis proposed that atomic mass and positive charge were evenly distributed, much like a diffuse pudding. This meant that nothing within the atom was dense enough to alter the path of an alpha particle. On the right, Ernest Rutherford's 1911 nuclear model completely challenged this assumption. He observed that some alpha particles bounced back, leading him to conclude that 99.9% of an atom's mass is concentrated in an incredibly small, dense core, with the remainder consisting mostly of empty space. As Rutherford famously stated, this result was as astonishing as firing a 15-inch shell at a piece of tissue paper and having it bounce back to hit you. Between 1917 and 1919, Ernest Rutherford achieved what medieval alchemists could only dream of, the first artificial transmutation of an element. In this historic experiment, Rutherford bombarded dry nitrogen gas with high-speed alpha particles. The violent collision shattered the nitrogen nucleus, fundamentally altering its structure and creating an oxygen isotope. This impact also expelled a fundamental, positively charged building block of matter. By successfully transforming one element into another, Rutherford became the world's first true alchemist. Recognizing the significance of the ejected subatomic particle, he officially named it the proton in 1920, marking another monumental milestone in nuclear physics. This timeline is structured as a 20-year syllabus that maps the historic deconstruction of the universe through concentric rings of discovery. It began with Ring 1 in 1899, which established that matter emits alpha and beta radiation. Ring 2, introduced in 1902, demonstrated that atoms can decay and transform through radioactivity. By 1911, Ring 3 revolutionized earlier models by revealing the presence of a microscopic, massive center known as the nucleus. In 1919, Ring 4 marked the discovery of the nucleus's positively charged building block, the proton. Finally, in 1920, the outer circle highlighted the prediction of a missing component, a neutral particle with a mass of 1 needed to prevent the nucleus from destabilizing, the neutron. In 1919, Ernest Rutherford succeeded J.J. Thomson as the director of the Cavendish Laboratory at Cambridge, marking the beginning of an exciting new era. It was here that his brilliant Russian protege, Pyotr Kapitsa, famously nicknamed him the crocodile, a creature symbolizing massive, unstoppable momentum that only moves forward, instilling both fear and respect. Rutherford operated like a loud and boisterous general. In fact, the laboratory culture necessitated a prominent "talk softly please" sign, primarily to protect sensitive scientific instruments from his booming voice. Despite his commanding presence, he was universally loved by his staff, always willing to allocate all available laboratory resources to support promising new ideas. This diagram illustrates the Cavendish family tree, highlighting Ernest Rutherford as the central figure in a remarkable scientific legacy. Surrounding his leadership are legendary physicists who transformed modern science. Among them, James Chadwick is credited with discovering the neutron in 1932, while Cockcroft and Walton were the first to artificially split the atom with a machine in the same year. Niels Bohr integrated quantum theory into Rutherford's atomic model, Patrick Blackett visualized transmutations using a cloud chamber, and Francis Aston refined the mass spectrometer to identify stable isotopes. Collectively, this influential network reinforced Rutherford's true legacy, facilitating the significant shift from individual tabletop experiments to the collaborative era of modern big science. This slide highlights the year 1932, known as the Annus Mirabilis or miraculous year, which brought three groundbreaking advancements in physics. First, the missing puzzle piece was found. After a 12-year search inspired by Rutherford's predictions, James Chadwick discovered the neutron. This discovery unlocked the ability to bombard atomic nuclei without encountering electrical repulsion. Second, we saw the emergence of large machinery. John Cockcroft and Ernest Walton constructed a linear accelerator to fire protons at lithium, successfully splitting the lithium atom, which marked the end of the era of tabletop physics. Finally, antimatter was visualized for the first time. Patrick Blackett used a cloud chamber to capture the positron, providing the world's first physical evidence of antimatter. Together, these breakthroughs drastically changed our understanding of the atom. This slide highlights Ernest Rutherford's influential role in science, focusing on three main pillars. First, under rescuing intellect, we see that in 1933, as president of the Academic Assistance Council, he led efforts to rescue and resettle hundreds of displaced Jewish scientists fleeing Nazi Germany, thereby preserving European intellectual talent. Second, under championing equality, he actively campaigned for Cambridge University to grant women full academic privileges equal to those of men, thereby supporting the careers of early female physicists such as Harriet Brooks. Finally, through public science, he served as president of the Royal Society, defended the editorial independence of the BBC, and utilized radio broadcasts to make the public's understanding of modern physics more accessible. This concluding slide pays tribute to Ernest Rutherford, aptly titled "The Man Who Made the Wave." In recognition of his monumental contributions to science, Element 104 was permanently named Rutherfordium in his honor. Upon his death in 1937, he received the rare distinction of being interred in the nave of Westminster Abbey, resting eternally alongside the giants Sir Isaac Newton and Lord Kelvin. This slide captures his legendary, confident spirit in a final exchange with a colleague. When a peer remarked, "Rutherford, you were always on the crest of the wave," Rutherford boldly replied, "I made the wave, didn't I?" A testament to a man who truly shaped modern physics.